Hello class, it's Computer Science Foundations, Paul Austin here, and we're going to look at complex numbers in Python today. So just to review a bit, we've been playing around with the types, Boolean, true and false. We've dealt with ints and floats. We've seen little lisps, some tuples. You don't know those, but those are the colors, range, and strings. We've dealt with that. But there's another numeric type called complex. You may have seen it in some of your algebra or calculus class. It's one of the primitive types in Python, and there's only a few computer science languages that have complex built in. But it's a kind of indication of how the language came about. Just to look at this here, this is a way of different languages coming into being. So the computers built back in the 10s, 30s, 40s, 50s, but let's get into the 60s and 70s. We have a PDP-11. It's in the era when a lot of computer languages were starting to show up, because without them, people had to flip the switches. And I'm looking at it on here, and there are switches, like lots of switches. You can toggle in the individual values and say, okay, that's one instruction. It's like having to spell a word or write a book, literally one letter at a time. But let's digress. That wasn't so good. And then there was assembly language, a lot better, but if you think of who's trying to write it, only a very few people ever really want to write assembly language. I don't know if anyone really wants to. Only the people who had been writing binary code going, assembly, so much easier. Well, then we have languages. There's several I'm not covering here, important ones like Lisp and Fortran. But C, that's why the PDP-11 is there. It was probably a good example of a language written to be very friendly to people, but very close to the hardware. So people didn't have to understand how memory was laid out. They didn't have to know the low-level pieces. They could write code that was, honestly, it's still one of the strongest languages that's still out there. And that's what a lot of operating systems are still predominantly done in C. But if you weren't trying to write a program for a computer, but rather you had a high-level numerical problem to solve, then you still didn't want to think about the hardware. And that's where languages like Python come about. Python languages are definitely targeted to be as close to the people as possible, and not just people who are programmers, people who are scientists and engineers. Even students are curious about how the programming works. So that's why it skips a lot of things, like a lot of extra punctuation and curly braces that you're going, wait, why do I need that? So just as a touch, there are other languages. There's lots. I could fill this whole screen with them. The position here doesn't mean a whole lot other than that C++ certainly grew out of C. So it tries to abstract more, but it still has C to its roots. And JavaScript, I'm not sure exactly where to put that on there. It's certainly much friendlier for people to use. It's very high level, but its first and foremost goal is to make web pages work well. And so that pulls it in some of its own directions. Oh, pardon me there. I hope that cough's okay. I'm glad I'm at home. So let's just look at what we've been doing. We've done a lot of turtle graphics, and a lot of those have had our move to and line tos, and you've seen us drawing things like lines, like these arrows here. I should have my water. Where's my water around here? Here we go. So when we draw those, we always have an X and Y coordinate that we're drawing to. And that X and Y pair is actually very similar to the way complex numbers are considered. So when you think of us moving a line from here and we're going to like 3, 5, that's also commonly thought of as like what a complex number, which would be 3 plus 5i. Well, Python, they're actually using the J. That's why I have the notation here. A bit more on that in a second. So all the time we've been thinking about having an X and Y, we could have just considered it a single number, a complex number. That's the number that has the square root of -1 in it somewhere. But when we think of it, and this is the trick, if you think of a complex number as two parts, like as in with a comma between, it gets a little confusing. Because if you look at it just as a vector, that's what this line is here, as a vector, it's a single concept. Don't try to split it up. The splitting up is more of an artifact. Because if we looked at, suppose we're doing multiple vectors, Here I've got one sort of like, it's something like pulling that origin over this way. And then maybe I've got another one pulling it over a little bit this way. And it's like, well, what happens if I'm adding those two vectors? Now, we didn't do that on our drawing, but that's one of the things, it's a fundamental thing of what people do with vectors. An example of how that would work is if I have different forces, I'd be going like, well, if A is pulling it this way and B was pulling it this way, if I add them together, isn't that the same as C being pulling it in another direction? And to make it a little more clear, suppose I have Mike pulling a sock to the left, and I have Boo pulling it up to the right. It's like, and they're both tugging at it, but it's like Sully goes like, hey, you guys sit down. I've got this covered. I'll just do it, and I'll pull it, and I can do the same work as both of you. So vectors show up a lot when you're in physics, even more so when you're dealing with fields like electric and magnetism. And in those cases, if you had to think everything of x and y pairs, you'd end up with lots of variables and lots of multiplications. But if you just think them as a vector and say, okay, C equals A plus B, then everything keeps simpler. And that's the point here, is that when you work with complex numbers, a lot of math stays much simpler than if you kind of looked at it as just the Cartesian plot that we're used to thinking about. Now that addition was pretty straightforward. But what if I want to do multiplication? And it's like, I'm not going to dive into a whole lot of that here. But just as the answer, the answer of C equals A times B, this is where C would end up at. And you're like, how did that happen? Well, again, I'm not going to cover it all in here. But the short of it is, if you're looking at how it works when you're dealing with magnetic fields and electric fields, is you actually take the angle of one and the angle of the other. That's where I got the blue part here, and I got the green part here. And you add them, this would be the angle of the final. And the length of C, of vector C, is going to be actually the product of this vector's length plus this vector's length. We could have figured that out with the Pythagorean theorem and added it. In fact, if you break it down, that's what's happening. But this multiplication, when you look at it in little pieces, it does start to get a little bit lengthy. And now, again, we'll just take a real quick glimpse at it. And I know I need to slide my screen over here. Can I do that? Yeah, I'll move it over here so you guys can see that. All right. You'll probably run across the term FOIL. So I guess what I was just going to do here is a little comparison. Just look at this one. When I'm seeing that 4 plus 2j times 3 plus 5j, or I, for the mathematician's point of view, I could kind of consider it and say, like, you know what? The FOIL, or the first, outer, inner, last, really it's something you've already been doing ever since you learned how to multiply like 2-digit numbers. Because consider 42 times 35. Well, what would you do? Well, you'd do something like 5 times 2 plus 5 times 4. And then you'd do 3 times 2 and plus 3 times 4. But you'd shift it over a digit. And you add it up and you get 1470. Now maybe the new math has a way of doing it, but it's probably just an estimate. So I could also express this kind of as a binomial. So I have 2 plus 40 times 5 times plus 30. And if you break it all out, these are the firsts, these are the outers, this is the inner, and this is the last, and lo and behold, 1200 plus 200 plus 60. Whoops, that should be a 10. Did that slide before. There you go. Fix slides on the fly. And so this is sort of what happens when you're doing that multiply of the complex number. Well, all right, we're going to look back at that Mandelbrot example we had. And before we leave out, we want to say thank you, Mike, thank you, Sully, and thank you, Boo. They've been a big help to us for here. So let's look at the sample code we have. And I'm going to take my screen here and put it back on the side. Are we good there? All right, we're good. All right. So our for loop, we've got that simple one at the end. It's just doing 4x and 4y. So we're doing it. It's going to make a grid. For each of those, we're going from that minus 200 to 201. So we're going to cover each point. And we're going to step by a resolution step. You'll find out for this one, it's nice to do it in larger chunks. So I'll start off with 5. But we do that loop, and for each one, we're calling pixel color. In pixel color, this is where that complex number starts to show up. I'm going to take the x and y, which was going from those large numbers from like negative 200 to 201, and we're going to scale it down to a -1 to a 1 range. And for the x, I'm even going to offshift it by another half. So this is where I'm taking what was x and y, two different concepts, sort of two independent variables, and I'm turning them into a single concept, the variable c. And that is a complex number. So we pass that into Mandelbrot, and this function is simply going to iterate. It's going to take a variable z, and it's going to start off in saying, well, z equals z squared plus c. That's kind of like that, I plus equals 1, like you're doing an increment. It's a little bit like, or maybe a multiply equals, but in this case we're doing it on a complex. So there's a lot of additions and multiplications happening right in this line. If you were doing it x and y, it's a lot of variables, but it's simpler. And then we're going to take, we want to take the magnitude of that real number. And so we'll take the real part squared and the imaginary squared, and then we'll do a square root of it. Notice that hypotenuse, the Pythagorean theorem. And if the number becomes too large, it's going to, what they say, escape. The number will actually get asymptotically larger, and it's not interesting any longer. So let's go run that program quickly and see what it looks like here. And there, this is actually what Benoit Mandelbrot saw when he first ran the program. Came out on a printer, and the technicians thought it was fudgy, so they kind of tried to clean it up, and he had to do it a few times before he actually got to see the picture he wanted to see. Now, here's a bit of how the complex numbers make things even easier. I wrote this code, I looked around different samples, and I saw that, and I said, now wait a second, and I'm scratching my hat through my heavy helmet here. Back to this the keynote here. We look at this guy here. The absolute value of a complex number is its magnitude. That's the length. That's the length of that vector. Remember, that's where we multiplied A's length times B length to get C's length. Well, that's the beauty of what it means when your paradigm is consistent throughout. I could actually kind of throw this line of code. I'm just going to say if abs of z greater than or equal to 2, put the colon, and I can throw away all of that. And we're going to go ahead and stop the old one and run the program again. And there's the exact same code. So in the complex domain, when we're talking about absolute, that is exactly what the magnitude is. So this is basically, in short, this is an example of, by providing a built-in type fundamental to the language, like complex numbers, it means the language is just easy to use by scientists and engineers when they're working with something that is best described as working with vectors. I think, a last bit I had for you guys on here, just to include examples. The Python will run super fast. The graphics we're dealing with, the turtle, it's modest. It does what it does well, but it doesn't do bitmaps extremely well. So here's a little viewer you can run online, and we could zoom in on little tiny sections and go like, what's going on down here? And if I looked at, this is an area that on the main one is like the sea of seahorses, the valley. But if you come in, this is off another one here. It's distinctly different. All right, well, that concludes this quick intro to complex numbers and the Mandelbrot set. Is a beautiful way to sort of appreciate what goes on. You'll definitely encounter complex numbers if you go into fields of engineering. All right, thanks, blessings, and have a great day. Bye.